Deriving the complete response for an RC circuit. To determine the complete response function, we start with the circuit that we did earlier in the first lecture. So I'm just going to paste that in since we've already drawn it out. So I'm going to use this circuit right here. So in the previous lecture, we said that there was going to be a series of circuits that we had to solve. So let's go through that. So the first thing that we need is that we need to look at circuit number 1. In circuit number 1, we are solving for VC of 0 minus. And of course, this happens before the switch is thrown. So let's do that. At t equal to 0 minus, the capacitor is replaced with its steady state equivalent. And we solve for VC of 0 minus. So since I already have the circuit, let's paste this in and modify it a little bit. So if I modify it, there is no switch. This is the way it is. And we need to create an open here. So if I create an open, I'm looking at this guy right here. So now that I have an open, I'm looking, I'm looking at this open right here. And as a consequence, we're calling this VC of 0 minus. So now let's go upload this up here so we can look at that. What we see here is that resistor 3 is in parallel with the capacitor. And because they're in parallel, they have the same voltage. So R3 is parallel to C, which tells us they have the same voltages. So applying VDR, we see that the voltage of resistor 3, how about if I just call it 3, at 0 minus must be the voltage of the capacitor at 0 minus. And then just using the voltage divider rule, I have a series of resistors. And I'm only focusing on R3 right there. So that's the voltage. And that guy is what we were after. So that's our first circuit in order to get the initial condition. Of course, the complexity of calculating the initial condition is going to vary depending on the details of the circuit. Now, let's go to circuit number 2. So we are now we're looking at circuit. No, I don't need to number these up. How about we just say circuits number 2 and number 3. Here, we need to, in this situation, we're solving for the Thevenin parameters and VOC and RTH. Now, we're only interested after the switch is thrown. So let's go do that. So what we are looking at is that at t equal to 0 plus, the switch kills off resistor R1, and here is the resulting circuit. So I still have the image, so I'm going to use the image and modify it. So if I come back here and paste it, here's this. So you can see that resistor when that switch is thrown, but this resistor is just gone, right? That resistor is just gone. So what I'm going to do is that I'm going to move this over. And this is my resulting circuit. This is my circuit that has to be converted. So then we could say that to convert this circuit into a Thevenin RC circuit, we need 2 separate circuits. And as we've already stated, one of them has to be for VOC and one of them has to be for RTH. So here we go. Let's start with circuit number 2. So this here, I'm going to say is the VOC circuit. And this is the one that we're going to look at here. So I'm going to remove the load, right? So the practice here is that you remove the load, the capacitive load, and calculate VOC. So if I copy this circuit here and I place it right here, I have this circuit, and what happens is that I now have an open which is now VOC. Now you could see that R3 is parallel to the open, so I could come in here and I could use VDR. So I'm going to use VDR because that's the voltage of the 3 here. So then I'm going to say that the voltage of the 3 at 0 plus is going to be the same as VOC, which is then equal to this. So then we're off to the second circuit here. And if I'm off to the second circuit for the Thevenin parameters, then we're going to call that circuit 3. And this is the RTH circuit. So this RTH circuit, remember we have to do what? We have to short out the power supply, okay? We have to short out the power supply. So I have an open here, and then I have no power supply, and then I replace it with a short here, and we are interested in this RT Thevenin resistance. So when I'm looking at this, you could see that R2 and R3 are in parallel. So these are parallel resistors. So if they're parallel, then I could say that RTH has to be these guys in parallel, which will then read R2 plus R3 in the denominator, and then the product of the two right there. So now I've solved my third circuit. So I don't consider the Thevenin a circuit that you have to solve for because we already have all the parameters. So now we have a Thevenin RC circuit. So if I draw this out, it's going to look something like this. I'm going to have my source, which is VOC. My capacitor, where I'm going to call this RTH. This is my capacitance C, and the voltage of the capacitor will be exactly the same voltage in this circuit right here, where now we have the Thevenin parameters. And our Thevenin parameters, we already see that VOC is then going to be R2, R3, divided into R3. That's V source. And then I'm going to have RTH, which will then be R2, R3 times the product of the two. I have that. So now that I have that, that circuit is always going to be the same. So in summary, although the details of VOC and RTH will change because it depends on the particular circuit that we're dealing with. The Thevenin RTH circuit will always be the same. It does not change. Therefore, solving for the capacitor's voltage will always have the same functional form.